So, a very good evening, everyone. Today we will be discussing on a very interesting topic from the subject heat transfer. Let's move on to study and analyze the heat exchangers. Heat exchanger is a practical application of what fundamentals we have gained from the study of thermodynamics and the application subject, that is the heat transfer. As the subject's name suggests, heat exchanger. Let's segregate this thing title into 5 different components. The first, heat. Now, the second one is temperature. Third one is a fluid. Then steady. And the last one, adiabatic. So before going into the fundamentals of the heat exchangers, its applications and its relevance, let us first analyze these 5 segregators in details. So let us move towards analyzing heat. So what heat is basically? As we all know, heat is a form of energy. So heat is a form of energy which is transferred from one system to another, and the driving force for this transfer is the temperature difference. That means suppose here is a system named A, another system named 2, and there is a transfer of energy between 1 and 2, and the driving force for this transfer of energy is the temperature difference delta T. Then this form of energy is called to be heat. Now moving towards temperature. Temperature is a very interesting terminology that we come across a day-to-day life. Just like now we are having summers and it is at its peak in such soon month. So we say the temperature is too high. In Decembers or winters, we say the temperature is too low. So primarily most of the misconception in amongst us is what temperature is that if we means a degree of hotness or coldness of a body. Okay, because if we are feeling something is hot or we are feeling something is cold or something is at a higher temperature, something is at a lower temperature, misconception is that we call it as temperature. But no, what temperature practically and physically means. Temperature is not the degree of hotness or coldness of a body, because this room, suppose it is maintained at 30 degrees Celsius, and this is a blackboard that I am having here. I will touch the blackboard, I will feel quite colder or lower as compared to if I will touch this plastic, because of the material property. So this body and this plastic thing is in equilibrium with the ambience. However, when I am touching it, it is giving me different feeling of the high temperature or low temperature thing. So we cannot say temperature is the degree of hotness or coldness of a body. So what temperature is? If we will move on analyzing the temperature, let's recall the 0th law of thermodynamics, which is the basics for understanding what temperature is. So what does the 0th law of thermodynamics says? Suppose there is a system A which is in thermal equilibrium with system B, and suppose there is a system B which is in thermal equilibrium with system C. That means system A will be in thermal equilibrium with system C. This is what we recall from the 0th law of thermodynamics. Here, if the equilibrium parameter between this thing is thermal equilibrium, then the property which remains same for this is temperature. Hope I am clear. I will be dictating it on, but let's first understand what the thing is. So now we are clear about what temperature is. So now let's start with from heat. So heat is a form of energy which is transferred from one system to another with temperature difference acting as a driving force. What is temperature? When two bodies are in thermal equilibrium with each other, then the property that remains same for both the system is temperature. Now moving towards fluid. What fluid is? So basically, again a misconception, if we will say anything that flows is fluid, but molten metal also flows. True, we say it's in molten state. fluidized state. But what basically fluids means, being an engineer, how should we go and define what fluid is? So going to the basics of the fluid mechanics, if we will define what fluid is a substance or a property of a matter that deforms continuously under the application of shear stress, however small be the magnitude of stress may be. Supposing if this white box that we can see is a fluid particle, and I apply a very minute magnitude of shear stress to that, then a deformation is observed immediately. Such kind of physical state is called as fluid. Fluid are primarily of two types. We can classify it as liquids and gases. So what fluid is? Fluid is a matter that deforms continuously under the application of shear stress, however small the magnitude of stress it be. So if we'll move on to the Newton's law, shear stress is equals to mu du by dy. It is for the Newtonian fluid. So here till now we analyzed what heat is, what temperature is, what fluid is. Excuse me. Now moving towards, what do you understand when we call a systems to be steady? Suppose something, now we understood that fluid is something that deforms continuously under the application of shear stress, however smaller the magnitude of shear stress be. Moving towards the steady, now let us analyze. Suppose an object is moving, let it be a fluid or solid, anything, it is moving. It is moving in such a condition that its property is not varying with time. Such type of systems are called to be steady system. So what a steady system is? When a quantity flows per unit time through a section is constant, it is called to be steady. Now moving towards the last parameter, that is adiabatic. From basic thermodynamics we can say a system is called to be adiabatic if the net, we write, heat transfer is zero. That essentially doesn't mean that there won't be any temperature. Temperature difference will be there, but there won't be any heat interaction to and from the system, or the net interaction of the system will be zero. So here comes the question, why, before getting into the topic of heat exchanger, we have analyzed what heat is, what temperature is, what fluid is, what do we mean by steady state, and what do you understand by the adiabatic system. So using all those 5 terminologies, now we are going to define what heat exchanger is. So heat exchanger is a steady flow adiabatic device in which two fluids flowing at different temperature exchange heat between them without any heat interaction to or from the surrounding. So what heat exchanger is? Heat exchanger is a steady flow adiabatic device in which two fluids flowing at different temperature exchange heat between them without interacting with the ambience or without making any transfer of heat with the ambience. That means suppose we consider a system, a fluid is flowing in this way, another fluid is flowing in this way. Suppose it is the T hot and in the inlet case. Suppose this is the T hot exit case. I stands for the inlet, E stands for the exit. Similarly, T cold inlet and T cold exit. Supposing if this is a steady flow adiabatic device in which hot fluid is flowing and cold fluid is flowing, and these two fluids are interacting with each other in terms of exchanging heat between them without causing any heat interaction to the ambient, then such system is called to be an heat exchanger. So hope I am clear about what this heat exchanger means. If we'll move on to the practical application of heat exchanger, you people must be acquainted with the fundamental TS diagram of a normal supposing say Rankine cycle. So temperature, entropy, because this is the dome. Then we know economizer, boiler, superheater, turbine, condenser. Let's touch it here like 1, 2, 3, 4, 5. So by pump work, supposing if we are making this fluid to go into this section 2 to 3, this 2 to 3 in a power plant is termed to be economizer. 3 to, supposing if here 3 dash, phase change is taking place. So here it is a boiler. 3 dash to 4, again temperature is increasing, it is superheater. And from 5 to 1, condenser. So this economizer, you can see it is increasing the fluid's temperature. Here also the temperature change is happening. It is also increasing the temperature. Here the temperature is decreasing. All those components are the best example of heat exchanger. Apart from that, if we'll move on, you might have heard about the energy storage devices. Energy storage devices. And we are also aware about distillation systems. All those things are very good example of a heat exchanger. So now let's move on towards analyzing the heat exchanger's perspective on the basis of the first law of thermodynamics. So we have started with the zeroth law of thermodynamics. We understood what heat is, what temperature is, what fluid is. Then we analyzed what heat exchanger is. We agglomerated some of its applications, that okay, these are the heat exchangers that we come across in our day-to-day life, in textbooks or somewhat in our laboratories. So now let's us move towards analyzing the application of first law of thermodynamics towards analyzing the heat exchanger. So we will be moving towards the application of first law of thermodynamics in analyzing heat exchanger. I am writing HE as an abbreviation towards the heat exchanger. So now let's just move to analyze what first law of thermodynamics basically says. From 12th fundamentals to the engineering fundamentals, first law of thermodynamics basically says the conservation of energy, that the energy can neither be created nor be destroyed, but it can be transferred from one form to another. That's fine. Let us write this thing mathematically. Here comes an interesting aspect. Energy can neither be created nor be destroyed, but it can be converted from one form to another. So mathematically, I can write here, it's a very dou q is equals to du plus dou w. Mathematically, I can express first law of thermodynamics in this form. Here, questions comes why I am using two different differential signs over here. Here it is d, but here it is dou. What does this signifies? Here comes the property aspect that we studied in thermodynamics. Heat and work are path functions. They are indefinite integrals. Internal energy is a point function. It's a definite integral. It's the property of a system. That's why work and heat that is shown are always designated in terms of dou, because of its indefinite integral condition, and du is because of its finite differentiation or definite integration. So from here we know that if we'll move on to the steady flow energy equation, we all are good aware about this steady flow energy equation. What does it say? That the net accumulation of the energy, that is, supposing if this is a system, the net energy inflow will be equals to E in will be equals to the net energy output across a system. So this thing I will be expressing in the terms of equation. So we will first move on to the H, enthalpy, plus V square by 2 kinetic energy, potential energy, Q, that is being given to a system. Suppose H1, V1, Z1, Q is equals to H2 plus V2 square by 2 plus GZ2 plus W. Okay, so this is what we understand from the steady flow energy equation. So please note it down, because we will be shifting to next page and we will be deriving how this heat exchangers is being applied or being analyzed by using the fundamentals of first law of thermodynamics. So H1 plus V1 square by 2 plus GZ1 plus Q is equals to H2 plus V2 square plus GZ2 plus W. Now moving towards the system, let's understand some of the basic assumptions that we take in analyzing this heat exchanger problem. So the assumptions that we make, number one, it is in the definition of heat exchanger, what? It is a steady flow adiabatic device. So the flow is steady state adiabatic. The condition is adiabatic. The fluid is flowing through a channel carrying a particular temperature, or there is a fluid that is flowing and the fluid has certain temperature. We will assume that the temperature of the fluid is uniform throughout its composition. So the temperature of fluid is uniform. So next, the fluid is flowing through a pipe. That means there will be some pressure, and we will assume the fluid is flowing at an uniform pressure. One more important aspect, the fluid is steady, the fluid is flow, the system is adiabatic, the fluid that is flowing having uniform temperature, there is no pressure gradient within the system, and it is a system. Let it be a metal or a ceramic kind of thing, mostly a metal thing, metallic thing. Suppose in a metal, fluid is flowing. Above the metal, there is another fluid. So there will be some contact resistance because of this material that is making some hindrance towards the transfer of the heat between the two fluids. So here comes the resistance or the thermal resistance that is provided by the material of the heat exchanger. The thermal resistance is uniform, or there is no abrupt changes in the thermal resistance. So these are the assumptions that we will be considering while analyzing the heat exchanger. So here, if we will remember, steady state, no variation with time, adiabatic, no heat transfer, temperature of the fluid is there, fluid is flowing at a uniform pressure, and the thermal resistance is uniform. So while applying all those assumptions, what we found that in the steady flow energy equation, if we will move on to that, so here H1 plus V1 square by 2 plus GZ1 plus Q is equals to H2 plus V2 square by 2 plus GZ2 plus W. These kinetic energy and potential energy, heat and work, all those terms can be neglected. Once it is neglected, what we come across to know, H1 is equals to H2. That means H1 minus H2 is equals to 0, which implies delta H is equals to 0. So what is this enthalpy? That means, so if the net H is equals to 0, that means the enthalpy change of the hot fluid and the enthalpy change of the cold fluid is equals to 0. Isn't it? So this implies I hope this much is clear, and if okay, I will explain this term again. Hope I am clear up to this point that the net enthalpy is 0. So that means if this net enthalpy is 0, that means I can write enthalpy during hot fluid. What is this? Plus the enthalpy of cold fluid will be equals to 0. Once this is equals to 0, what we will do then? Then this hot fluid and cold fluid, this we can write mCp hot into Thi minus Thi plus m dot Cp cold Tc. Okay, now here comes the question, what I will take, whether I will take Tce minus Tci or Tci minus Tc. Now let's initial minus because heat is being lost from the system. The quantity itself designate the heat is losing, and from the thermodynamics application, if we will understand, we know heat added to a system is positive and work done by a system is positive. So this is equals to 0. That means if I will move, what I will know, minus of, I can write m dot Cp hot, Thi minus Thi is equals to m dot Cp cold Tce minus Tci. What does it represent? The heat that is being transferred from the hotter object is being gained by the cold object, or the hotter fluid is ejecting the heat and the colder fluid is absorbing the heat. So it is basically what our purpose is, heat exchanging. We will absorb the heat from the higher body and will transfer it to the system which is at a low temperature condition. So it satisfies that. From here, what we come across to know, that the heat that is ejected from a hotter object, heat loss, is gained by the heat in a colder object. Here the product m dot and Cp, this m dot and specific heat of a system is called as heat capacity. It is having a very practical relevance, which will subsequently we will be studying. So mCp is called as heat capacity. So from here, from the fundamental of thermodynamics, you come across to know how the heat exchanger works. So here, if we will say, okay, this is mCp. mCp is for a substance which is having in a particular state. If phase change is happening, what will happen? Does a steam, or during a phase change process, how are you going to estimate this specific energy? So in that case, what we will be considering, one factor will be coming into picture. What is that? Dryness fraction. Another aspect, latent heat of vaporization. So those things will come into picture, and that needs a very depthful analysis, and we will be studying it in subsequent classes. So here we analyzed about what the fundamental of heat exchanger is. Now, so till now what have happened, that we have studied what heat exchanger is, what are the basic segregations or terminologies that we should analyze while studying the heat exchanger, and how this heat exchanger is being applied in our day-to-day applications, like we studied economizer, preheater, superheater, boiler, distillation unit, thermal energy storage units. Then we moved on towards analyzing the application of first law of thermodynamics, towards analyzing how the heat transfer is taking place. Now let us move towards analyzing classification of heat exchangers. Here I will tell an important thing, that if you are going to study this heat exchanger in a depthful manner, so I will suggest two books, textbooks that are very good. One is In Corpora David, another is Sengel. These two books are very good for understanding the heat transfer, and their problems are very good. Apart from your previous questions, if you are willing to study it from a depthful manner, you can refer these books. So classification of heat exchangers now we will study. So heat exchangers are primarily classified into three types. What are they? Number one, fast. It comes generators, then recuperators, and direct contact type, regenerators, recuperators, and direct contact type. So moving towards the regenerators. Regenerator means there will be a same surface. This same surface will be having some cellulose heat capacity matrices in which there will be two different fluid, that is the hot fluid and cold fluid will be flowing. Suppose it is TH inlet and this is TH exit, and similarly this is T cold inlet and T cold exit. So a system in which the same surface area is exposed to both hot and cold fluid simultaneously one by one, and there have those sorry so if we will tell this, these are high heat capacity matrices. So here what will happen, the hot fluid will flow through the surface area, this cellulose matrix will absorb the heat from there and the hot fluid will exit. Then simultaneously cold fluid will flow, that cold fluid will extract the heat from the cellulose matrix and it will flow. So here the continuous cycle, what it will make, hot fluid is going, energy is being carried away by this cellulose matrix, and cold fluid is going, it is absorbing the heat. So here these two hot fluid and cold fluid are not coming in direct contact to each other, but they are exposed to the same surface area in which one by one, one after another, this fluid is flowing and it is absorbing the heat. So this is what regenerator means. Now moving towards recuperators. Recuperators are the heat exchangers in which simultaneously both the hot fluid and cold fluid are made to flow with having a separation between them. That means the hot fluid is flowing and cold fluid is flowing, but they are separated by some wall. That means this wall act as the media for the exchange of heat from the hot fluid to cold fluid. So in the regenerators, it is one by one, one after the other, you are making the fluid to flow. In recuperators, you are making the excuse me, the fluid to flow simultaneously and you are transferring the heat. In the direct contact type heat exchanger, what happens, you make the hot fluid and cold fluid to come in contact with each other in one go. That means in this case both the heat transfer and mass transfer takes place simultaneously. Heat transfer and mass transfer takes place simultaneously, and this heat transfer and mass transfer in a system that is taking place, we know, we have seen, is cooling towers. What can be the example of a recuperator? A recuperator's example is a double pipe heat exchanger, tail and tube heat exchanger, plate type heat exchanger. Again, here the flow direction can be altered, that we'll be analyzing next. Another example, an example of this regenerator is L Ljungstrom air preheater used in turbine power plant. So these are the classification. Now we will move on towards analyzing these recuperators. As you see, double pipe, saline tube and plate type heat exchanger are there, and fluid is flowing through that, and a separation wall is there that is making the differentiation between the hot fluid flow and the cold fluid flow. So here we know one thing can happen. I can change the direction. Supposing if the hot fluid is flowing in this way, I can reverse the direction of the cold fluid, or I can reverse the direction of hot fluid. So here what happens, if we will analyze a system in which hot fluid is flowing in a direction and cold fluid is flowing in the same direction with a separation wall is there, this type of flow is called as parallel flow or concurrent flow. Understand? Similarly, if we will go to a system in which hot fluid is moving in one direction, whereas the cold fluid is moving opposite direction to the flow of the hot fluid, and there is a separation wall between them. In this case, this type of flow is called as counter flow or counter current flow. Another category of this type of heat exchanger comes into picture if there will be a heat exchanging device in which the hot fluid, supposing if it is coming in one direction, and the cold fluid, it is just coming at an angle of 90 degree or intersecting it, and it is flowing in such a manner. Such type of flow is called to be cross flow. Hope you are now clear with the classification of those heat exchangers: parallel flow or concurrent flow, counter flow or counter current flow, and cross flow. So these are the classifications and types of heat exchanger. Now if someone will ask, discuss the types of heat exchanger basing on the flow: parallel flow, counter flow, cross flow, basing on the design, double pipe, saline tube, or it can again be explained regenerator, recuperators, and direct contact type. So the classification of heat exchangers are done now, but here comes in the double pipe heat exchanger, or it be a saline tube heat exchanger, or it be a plate type heat exchanger, flow can be either parallel or counter. Cross have its own specific configuration of heat exchanger. That also example we will discuss subsequently. And among all those heat exchanger, there comes in nowadays a very good thing, as you might have known, that we are now shifting towards the nanotechnology. Okay, we have shifted towards nanotechnology and we are moving through that. So that means that we are doing miniaturization. During the miniaturization, the cooling need to be done in a higher efficient way. Heat exchanger will be there, but we need to have some high efficient heat exchanging equipments. So as the system size reduces, we have to make our heat exchanging system also compact or smaller in size. Such heat exchangers are known as compact heat exchangers. What is the compact heat exchanger? If the surface area of the heat exchanger to the volume of heat exchanger is greater than equal to 700 meter square per meter cube, then the system is said to be compact and the heat exchanger is said to be compact heat exchanger. Hope we are clear till this classification of heat exchangers.